Today we are solving the most famous first DSA problem, 2-sum. It looks simple, but it teaches one of the most important ideas in DSA, how to use extra memory to reduce time. This exact thinking appears again and again in arrays, strings, frequency counting, and hash map problems. So we are given an array, nums, and a target. We need to return the indices of two numbers is that nums I plus nums j equal target. There are two important conditions. We cannot use the same element twice, and the problem guarantees exactly one valid answer. So on LeetCode, we do not have to handle the no answer case, but in real interviews, we can still mention it. Let us take an example. Nums equal to 7, 11, and 5, 15, and target equals 9. Now 2 plus 7 equals 9. So the values are 2 and 7. But the question asks for indices, not values. So 2 is at index 0 and 7 is at index 1. So the answer is 0, 1. Now the first solution is very simple. Check every possible pair, pick nums I, then compare it with every nums j after it. If the sum becomes equal to the target, return I, j. The solution is correct, but the time complexity is order of n square. So this is the brute force where we compare each and every number. Its time complexity is order of n square. Because for each element we have to scan many other elements, and since n can go up to 10 power 4, and order n square solution can become very slow. As you can see the constraints. So num dot length is to the 10 power 4 order. That is why the follow-up asks, can we do better? So instead of asking which second number should I try, we should ask what number do I need? If the number if the current number is x, then the missing partner is target one is x. If my current number is x, so my target number is target minus x. Let's call this missing partner. So the problem becomes, for example, if target equal to 9 and my current number is 2. So the question becomes, so my missing partner is 7, and the question becomes, have I seen 7 earlier or not? So this is the main idea behind the optimized solution. To quickly check whether a number has appeared earlier, we use a hash map. Use a hash map. A hash map allows us to check existence in almost order one average time. So It has order of one, that is constant average time. It is almost. So we store numbers we have already seen along with their indices. The map looks like this. Value maps to index. As we move from left to right, calculate the complement. So as we move from left to right, calculate the complement. Check if the complement is already in the map. This is the first step. Second step is check if the complement is already in the map. Then third is if yes, return the answer. And if no, store the current number in the map. So let's try to run this example. So again, our nums equal to 2, 7, 11, 15, target equal to 9. So let's say the map is seen, that is empty right now. We go to index 0. We get x equal to 2. And what we need is 9 minus 2 equals 7. Is 7 in the map? No. So we store. So scene becomes, so 2 is the value and 0 is the index number. Now let's go to index 1. Now x equals 7. Need 9 minus 7 equals 2. So 2 is in the map. So it is present at index 0. So we return 0, comma 1. So notice that we found the answer in just one scan. The code idea is simple. First create an empty map, scene equal to an empty map. Then for every index I and number x, need equal target minus x. Now check if need in scene, return seed need, comma I, otherwise store the current number. The important point is check first, store later. Check first, store later. This is important because we might accidentally use the same index twice. And the problem clearly says you cannot use the same element twice. Now the time complexity will be the time complexity in this case equals order of n, because we are scanning just once, and to check if the need is there in the hash map or not, it takes only order one time. But the space complexity equals order n. It is not constant, but it is of order n, because we need to, in the worst case, we can store many numbers in the hash map. So the trade-off is clear. We use extra memory to save time. And this is one of the most important patterns in DSA. Now let's quickly write down the code. Let me comment this out. So let me go through this one by one. For I comma x and enumerate nums. So when you write enumerate nums, it makes it this is an array nums. So nums is 2, 7, 11, 15, for example. So what enumerate nums will do, it will transform it into like this: 0, 2, 1, 7, 2, 11, 3, 15. Basically the index, this is the index and this is the value, index comma value. So when I write for I comma x, that means the first I is the index and x is the value. I is the index and I is the index and x is the value in enumerate nums. So what we need is need equal target minus x. So that means if our target is 9, for example, then our need will become for x equal to 2, it becomes 7. And if need in scene, then we need to return scene and in square brackets need. So that will ensure that we are returning the index and not the value. So let's try to run this with the test case. And in the second case, if we are not, if need is not in scene, then we store the scene x equal to I. So by storing scene x equal to I, this becomes scene was initially like this. Now after the first pass, it will become scene equal to 2, 0, 2. So 0 is the index and 2 is the value. Let's try to run the code now. And all the test cases passes. Let's try to submit it and see. Okay, so it has been, all the test cases have been passed and we have written a good code. Okay, so this is one of the most important pattern in DSA. Whenever you see a pair sum type problem, remember this thought process. For the current number, calculate the missing partner. Then ask, has that partner already appeared? That is the complete two-sum pattern. Has that partner already appeared? That is the complete two-sum pattern.